as many situations as possible, as much practice at product and quotient rules as you can, because there are so many different things that could happen that there's no way I'm going to be able to cover every permutation. So when you do these, guys, will you try and look at these as just examples of things and processes rather than specific questions? So in this particular one, it's e to the power of p with a p times a p square root of p. So let's start with the obvious question. Product rule or quotient rule? Should be a no-brainer. Product. Agreed? There's definitely not a quotient. Less obvious. Not all the time, but this is one of these times. Don't you have to turn things into fractional powers of p so that you'll be able to differentiate later? And that's the strange issue. That's why I picked this one, because of this little guy, p square root of p. What single fractional power of p is that guy equal to? So p times square root of p. Here's a clue. P times p to the half. What single fractional power does that become? Okay, that's it. No more clues. 3/2, yes. Do you see, if you didn't notice that, wouldn't that question get really weird and really difficult? Because you wouldn't really be sure, how do I differentiate p square root of p? I guess you could go down this rabbit hole where you do a product rule, you know, and go really messy. Now, it's not pretty. I mean, I'm not saying this question's easy, because it isn't. But if we call this guy f and we call this whole thing g, we should then be able to do the differentiation. So the derivative is going to be f dash g plus f of g dashed. Well, when you differentiate e to the p, you get e to the p, and then you leave this guy alone. And then you leave the first one alone, and you differentiate this guy, and when you do it, you get, oops, almost made a mistake there, you get 1 plus, and if you differentiate this, the power rule says multiply by the power and reduce the power by 1. And so we're finished differentiation. Do you think that's going to be the answer, or should we be doing more next? You think that's good, or could it be made prettier? Think style points. Any suggestions?
You can still factor out the e to the p.
Okay. And if I do that, okay, they're all kind of jumbled up, but that's not really a big issue.
Style points to make it look like at the beginning, so square roots, cube roots. Those squares.
Okay. Square roots in this case with some cubes in it. Style points finished. You got it? Not a lot happened to that. Would you agree? Nothing got collected, nothing got cancelled. You know, it was mostly just pulling out an e to the p and then making it look like the original. Right. Some questions involve a lot more tidying up than others. I've seen questions where you're virtually getting nothing to tidy up. In other words, once you've written this down, it's done. You can't really do much to it. But that's kind of uncommon, but it can happen. So I chose that one only for that one feature. I choose this one for. Choosing this one because it has letters in it. Not the variable, but down here. There is nothing I need to change, so I can immediately go for this one. Would you agree that this is a pretty much obvious quotient rule? right? I don't think people get mixed up between when it's a product rule case and, you know, when it's a quotient rule. We agree one's a fraction and one a, right? It's pretty easy to see them in general. So in this case, it's going to be f dash g, take away f of g dashed, all over g squared. If you differentiate the top, you get that, and you leave the bottom alone. Take away, you leave the top alone. And now we've got to be careful. What do you get when you differentiate this term, these terms here, with respect to R? Okay, what does B get you, if anything? You differentiate B, what do you get?
Nothing.
Nothing. What do you get if you differentiate A, e to the R? A times e to the R, what do you get? Okay, if it was just e to the R, wouldn't you get e to the R? Okay, it's A times e to the R, so what do you get?
Do you multiply the R with the A?
Yeah, you just get that. So if it was 5e to the x, wouldn't you get 5e to the x as the derivative? If it was 10e to the x, wouldn't you get 10e to the x as its derivative? It's ae to the r, so you get ae to the r as its derivative. And then on the bottom.
Wait.
Hmm?
Sorry, I'm kind of confused.
Okay, look. Is it on this last bit, this ae to the r bit?
Well, I was just gonna say the B. I thought the
Okay, let's look at this as a separate question then, right? So imagine I asked you to differentiate this, we'll call it y. B is a constant. That means it's really just a number. And when I differentiate numbers, don't you always get 0?
all right, I got you.
Right. The only variable in this story is this guy, the r. So when you differentiate a e to the r, I'm saying the answer is a e to the r, and since 0 is there, that's what you get. Think of a as a number. Think of 5 times e to the r, or 10 times e to the r, or any number you like. And if the r's bug you, think of 3e to the x or 10e to the x. In every single one of these situations, if I differentiated them, don't you just get the same guy? Because if the derivative of e to the r is e to the r, shouldn't the derivative of 5 of them be 5e to the r's? Right, that's kind of the logic. So that's where that guy came from. Are we good? Right. On the bottom, you get a big ugly guy squared. So remember that the only variable here is r, right? Anything with an r is considered a variable. Now we have style points. I've never found a situation where foiling the bottom out is going to do any good. So I'm not going to do anything to the top, the bottom, but I'm going to do something to the top. What?
If I factor out the e to the r.
That's what I would suggest. And you're going to have a b plus an ae to the r. Subtract. Oh, that was nice. Did you see something nice happening here? Can I jump ahead of myself here? Doesn't that guy kill off that guy? So all that's really left is a b. It's a bit lopsided, but there is your answer. The derivative of this fraction is b e to the r over this guy squared. Would you agree style points have helped to make this question nicer looking? The answer. Any questions about that particular one before I move on to our next one?
So why could you not have multiplied out the e to the r, like distributed the e to the r within
Not a problem at all, Teresa. You'd eventually get them. You'd eventually get the same answer. So nothing wrong with that.
Oh, I see. I got you. Okay, thank you.
Right. So if your brain sees something one way and it's not necessarily the way my brain sees it, I mean, mathematically, she said, distribute, right? Right. Now, if you did it, you'd get BE to the R, AE to the 2R, take away AE to the 2R. The two terms at the end cancel, just like you did here, and she would be left with BE to the R. I don't know if you had time to try it out, but if you did, you'd see you get the same answer.
I just got done with it. Yeah, it's exactly the same. Thank you.
Right. So I was probably suggest, since that made more sense to you, or your brain seems better that way, why don't you just do it that way? You know, works, right?
Okay.
What's that saying I'm getting? There's more than one way to skin a cat. You ever heard that phrase? But don't skin cats, because cats are nice. 19. But I've chosen this one only to set it up. I'm not actually going to do all, whoops, there we go. I have to write it again. I've only got this set up. I'm not going to do the whole thing. And the reason is I just want to figure out how to deal with one problem, and that's all. That guy is not ready to be differentiated. Something needs to be changed into a form that's going to allow me to do the quotient rule, because it is a quotient rule question. What needs to be changed?
Remove the square root.
Okay, so that little 3 means it's a cube root. What fractional power is the cube root of t going to be?
The 1/3.
1/3. Now, will you agree, although that's ugly, isn't that the way it needs to be to do the f dash and the g's and all the stuff that's going to come later, right?
Mhm.
So, you know, quotient rule, do your thing. Right. Now, the next one, 21, wasn't anything. Oh, this is so cool. I love this question. You might not like it right now, but it is such an elegant question because it uses something that we haven't done, mostly because you don't need to. Would you agree that's a quotient rule? Agreed? It's a fraction. Would you agree that that looks a bit weird? Now, if I was writing it down, and there's nothing wrong with this, I could rewrite it as cx to the -1. You agree? And the top would be f, and it'd be this, and the bottom would be g, and it would be that. And you could do the quotient rule, and it would eventually work, and everything is perfectly fine if that's how you would tackle that. But this is an example of a situation which I have a name for. You know how I have names like, as long as you do it to both sides, it's okay rule, right? I make up names for things. This rule is called just because you can doesn't mean you should rule. And it comes from the fact when I was young, I used to sing in the shower. And my mum would come and she would bang on the door because I am a very, very bad singer. And she would say something like, just because you can sing doesn't mean you should, right? I had no problems with that because I couldn't sing. Now, I could do this that way. Can you trust me that that ends up being really ugly with funny negative powers, and the style points of it are horrendously messy? I mean, you'd get the right answer, but horrendously messy. I'm going to look at that and say, okay, I could do it that way, but it doesn't mean I should. Couldn't I simplify this fraction first? What special version of 1 would be a good thing to do to this fraction to make it nicer? A special version of 1. So 5/5 wouldn't do any good, but something over something would.
X over X.
Yes. Now, The two top guys are x squared. This guy becomes x squared, and this guy becomes plus c. Would you agree that this guy is going to be a lot easier to differentiate and a lot easier to make pretty, right? Style points at the end. Agree? So sometimes, if you can see it, you don't always see it, but if you can see it, can't you take something that's really ugly and maybe make it prettier before you even differentiate it? In other words, do some style points on it before you even differentiate. So that's just because you can doesn't mean you should. Let's show you another example of that situation. Would you agree that that is a product rule? And if I wanted to do it as a product rule, the only thing I would need to do would be to rewrite the square roots as fractional powers. And it's not the worst product rule in the world, right? It would work totally fine that way. But that's not the only way to tackle this question. So forget for a moment about differentiation. Just look at that expression. Is there anything you might want to do to it that might end up making it even nicer?
Multiply it out.
Okay. X times x is x squared. X times this guy is what? X square root of x. Going this way, it's negative x square root of x. And this guy times this guy, well, a negative square root of x multiplied by a positive square root of x gives you negative x. And guess what? It ended up just being x squared minus x. You see how easy its derivative was? These two kill each other off. The answer is just that. And the derivative of that is very simple. So just because you can doesn't mean you should, right? If you're not comfortable with the algebra that I've done here, you know you can still do the question the usual way, right? It's just going to take you maybe a lot longer, and maybe the algebra at the end will be very messy because you have to tidy things up, right, and make them look pretty. So it's not the end of the world. But if you can see it, it can save you a lot of time. Now we're going to look at a new idea. Multiple derivatives. Well, it's not quite a new idea because I'm sure I've touched on it somewhere. I'm going to make my life very easy by picking a very simple function to start with. That doesn't need a product or quotient rule, right? If I asked you to find its first derivative, that's its formal tail, you use the power rule, multiply by the power, reduce it by 1. Multiply by the power, reduce it by 1. The derivative of -1 is a number, so you got 0. Tell me I'm right. Did I ever mention second derivatives to you? If not, I'm about to tell you. You remember?
Not today. In
Okay.
the past,
In the past.
we did one.
We did one, right? So that was kind of out of sync. Now we're doing it officially. This is where they have. Right. If you wanted to find the second derivative, which is what you call that guy. Normally this one's just called the derivative because that's the guy you always get. But if you want his full title, he's called the first derivative. This guy is always called the second derivative. And don't you just differentiate this fella to get the second derivative? So you do the power rule. And I'll do one more. And the third derivative, multiply by the power, reduce the power by 1. Technically speaking, couldn't you just keep going till you get bored? So you could find the 4th, 5th, and 24th derivative if you wanted to. Okay, here's a trick question for you. When the derivatives get too big, in other words, there's too many of them, we put a little bracket around it and call it 20. So this is the 20th derivative. We tend to use Roman numerals, you know, for 1, 2, 3, 4, you know, because it's pretty easy to do. But after that, we tend to go this way. What is the 20th derivative of e to the x?
E to the x?
Yeah. Don't you like e to the x? Doesn't it make your life easy for lots of situations? Right. Now, multiple derivatives, that just means second, third derivatives typically of more difficult situations. That's the guy we're going to find the first and second derivative. For the first derivative, would you agree this is a product draw? You'll look at that and you say product draw. So it's going to be f dash g plus f of g dashed. Forget that f, that's a label. The derivative of this guy is 4x cubed. Leave that guy alone. Plus leave this guy alone and differentiate that. And when you do that, you get this. So far, so good. Now, if I'm doing style points, I'd pull out e to the x. Agreed? Anything else I can pull out as a common factor?
X cubed.
And that would leave me with 4 plus x. And if the question was asking only for the first derivative, that's exactly what I would do. But the question wants us now to get the second derivative. And because of that, don't we have to be a little bit selective about who we use? This is the first derivative, and so is this the first derivative. Do you see the problem with this function is it's not 2 things multiplied, isn't it 3 things multiplied? There's an x cubed, then there's a times e to the x, and then there's a times 40 plus x. Isn't the product rule only really designed for 2 things multiplied? So can you see how this form is not really any good to us? But you might say, well, God, that's not much better, which I agree. Would you agree that this is a product rule and this is a different product rule? So essentially, you don't have to do the product rule on this one and totally separate from it, the product rule on this one, and then add all the pieces. So do you see how ugly that's going to be? But that's how you have to do it. Would you agree you can't really do it on this because there's 3 things? We can talk about how we might get around that. So I'm going to use this version of the answer, which kind of means I'm going to have 2 product rules. That's going to be f and g for the first one, and the new different one is going to be those 2. So the second derivative is f dash g plus f of g dashed. I have a big long gap, plus f dash g plus f of g dashed. Differentiate this guy with the power rule, you get 12x squared. Leave the second one alone. Leave the first one alone and differentiate that guy. Derivative of the first guy, leave the second alone, that's g. F and the derivative of g. And now for the second derivative, I'm going to take that guy, that guy, that guy, and that guy, because I'm doing style points now, e to the x. What's the biggest power of x that I can pull out of these 4 terms as a common factor? What's the largest power of x?
X squared.
Agreed. Is there any multiples I can use? Not this time, no. So I'm going to have 12, used up, plus 4, and x left over, plus 4x, and plus an x squared. And I just noticed a little bit out of sync, but those 2 can be combined. And we now have that. And to be honest, if you got that far, I would be happy. But let's be nitpicky. Sometimes, just sometimes, you can do better. Do you notice that quadratic? It factors, doesn't it? What does it factor as?
X plus 2, X plus 6.
Now, I wouldn't ding you in a test for getting that far. Now, if you remember the rules, make it look like the original. Well, you get that for free. And shouldn't you factor the heck out of it, right? Would you agree that is as good as it's ever going to get factored? Now, in case you're wondering why we have that factor the heck out of it rule, why is that important? Well, one reason is it's so everybody gives the same answer. But the other reason is that very often you are interested in solving when are derivatives equal to 0. Because a derivative is the slope of the tangent line. And when you talk about slopes of tangent lines, aren't the tops of hills and the bottoms of valleys going to have 0 derivatives? Because their tangent lines are horizontal. So if you had a curve, wouldn't you be interested in where the hills and valleys are? Wouldn't that be a feature you'd like to know where it was? And if you factor it like this, can't you see pretty clearly where it's going to be? X equals 0, X equals -2, and X equals -6. You see, I can tell the X coordinates of hills and valleys of a function, in this case, that one, by using its derivatives. Well, actually, I should be doing it in the first derivative, but the second derivative tells you things as well. Now, that is totally fine. Do it this way. I'm now going to show you. Oh, I won't do f of x. That's just distracting. I'm going to do a y. So, in fact, I'm going to hide that question so you don't think it's connected to it. Imagine that you did a different derivative, right? And you got 3 guys again. Now, couldn't we simply just find the line above and use that? And that's what we did in the previous technique. I'm going to see if you can create from scratch a product rule when there's 3 things happening. And we're going to call them F, G, and H. Now, when it was 2 things happening, wasn't the product rule F dash G plus F of G dashed? Anybody think they could come up with what the rule for a product of 3 things is? And since you don't know, you're kind of working in the dark here, but there is a lot of symmetry to it, and there is a kind of clue here. Any ideas what the product rule for a 3 things multiplied would be? Have a shot at it. If you're wrong, you're wrong. No biggie.
Have to do the differential of each one and then. Okay.
Yeah, that sounds good. Keep going.
Oh, like FG derivative at H, and then do it again for each one until you've done, yeah, FG derivative H, and then do it again for H, yeah.
There is a formula that you probably won't see in a textbook, but that formula will allow you to differentiate 3 guys. Would you agree you know how to get all the pieces? Right, for instance, won't the derivative of that be 2x, won't g dash be e(x), and won't h dash be what, 15x squared? Can you imagine that although it is big, might that be a little bit less work than how we had to do it if we broke it into pieces and done each piece? So it's just a help. If you want to use this formula, go ahead. If you just want to break it apart and do 2 product rules, totally cool with that too, right? Just giving you an option. Some of you like things like that because you see it as a shortcut. Others don't because it's one more thing to add to their already crowded list of things that they need to remember. But at least it's an option for you. Oh, I should do a quotient rule, shouldn't I? Why do you think I hate doing quotient rules with first and second derivatives? Any ideas why I don't like doing them? Because I do have to do one. It's only fair that you see it.
Well, quotient rule is a little complicated in the first place.
Yeah. And it gets uglier when you do the second. And I'm a careless person. Not that you would know, because I never make mistakes, but I am. And there's nothing more frustrating than doing it correctly, but losing a 2 or a sign, and the answer's not right because of it. So this function does not look particularly weird, right? It's clearly a quotient rule. So doing a single quotient rule, I have no problems with, right? They don't tend to be particularly horrible. A little bit uglier perhaps, but nothing major, right? So the first derivative would be differentiate that, which is 1, leave this guy alone, take away, leave this guy alone, and differentiate the bottom. And the whole thing ends up being x squared minus 4 squared. And so I now have x squared take away 4, take away 2x squared, all over x squared minus 4 squared. And that becomes negative x squared negative 4 over x squared take away 4 squared. Not too bad, agreed? Technically, I could pull out a -1 as a common factor, but I don't think any benefit doing that. Now, this is where the problem starts. I need to do the second derivative. The top is all of that. Put a big bracket around it. That's f. The bottom is this guy. X squared take away 4 squared is the bottom, right? That's g. I can't use it when it's written that way. Right? We can't differentiate right now, right? We don't know how to differentiate x squared minus 4 squared. I have to find a different version of it. Once I've got that different version, then I can start with my formula for the second derivative. What do you think you should do with x squared minus 4 algebraically? What you should do with this to make it that I can now differentiate g, the bottom?
You got a FOIL?
Yeah, and you just trust me on this, but you can check it. Okay, now at this point here, would you agree that the second derivative is doable? It's just going to be downright ugly. And I've never seen many second derivative questions that use a quotient rule that are nice, right? They're just ugly and then they get really ugly, right? But I'll see what we can do here. Differentiate the top, it's negative 2x. Leave the bottom alone. Take away, leave the top alone, that's f, and differentiate the bottom, which is what? 4x cubed minus 16x squared. And then the whole thing on the bottom gets squared. Couldn't I put a bracket around that and square it? Right? This whole thing squared. But isn't this thing also him? So if you take that guy and you square it, can you see it turns into that guy in the bottom? Are you okay with that? That this guy squared is that guy squared, which is that. Does that make sense? Just to make it look pretty. Now, top line, yeah. Multiply out 2x to the 5 plus 16x cubed, take away 32x. Now be really careful, a lot of negatives going on here. That guy times that guy is negative 4x cubed, but then you subtract it is plus 4x cubed. That guy times that guy is not cubed, fifth. There we go. That guy times that guy is positive 16x to the 4, then you subtract it. This guy times this guy is negative 16x cubed, but then you subtract it. And the last one is positive 64x squared, but then you subtract it. Yep, this one is living up to what I thought. Would you agree the only thing left to do here is maybe collect like terms and then see if we can factor anything. So I have got that guy and I've got that guy. So that ends up being 2x to the 5. I have only one of these, so that's take away 16x to the 4. I have that guy and that guy, which are both positive, unfortunately. So I get 32 of those. And I get this one, and did I miss somebody? Oh, x squared. I get this guy. And then lastly, I got that guy. Yep, it lived up to its expectations of being really ugly. Is there anything you can do on the top row style point wise?
You get a 2x.
Yeah. It's almost not worth it, isn't it? But, you know, we should do it because that's the rules. So you take out an x and you got x to the 4. You got minus 8x cubed plus 16x squared minus 32x minus 16. And I'm finished. What an ugly question. There is nothing elegant about that technique, isn't it? Just brute force and be careful. Just messy from start to finish. Are we cool with first and second derivatives? You don't get a lot of practice, but you've seen essentially the technique. Anything you want to talk about here before we move on to our last short topic for today, and then we'll be finished. Okay, assuming that's good to go then. Now we know how to find the equation of a tangent line. The only difference here is that the functions that we're going to do it to are going to be quotient rules or product rules. So suppose you were being asked to do at the point P 1,5, right? So we're being asked to find the equation of the tangent line to this fraction, this rational function, at the point 1,5. What we need to do is we need to find m, which is the slope of the tangent line. And to do that, we find the derivative. In this case, it's a quotient rule. So f dash g, take away f of g dashed over g squared. It's 2x times this guy, take away x squared times that guy, all over x cubed plus 1 squared. So I get 2x to the 4 plus 2x, take away 3x to the 4. Not a lot happening here, but I have a 2x, take away an x to the 4. And if I pull out an x as a common factor, we get that. So we have the derivative. The derivative at 1 is what we're interested in. So it's going to be 1, 2 take away 1 cubed all over 1 cubed plus 1 squared. So that's 1. That's 1. That's 1 plus 1 is 2, and 2 gets you 4. So I get a quarter. So the slope of the tangent line is a quarter. The point that it passes through is that. Then we can use this formula, which you've seen before, called the point slope equation. And that's x1 and that is y1. So y take away 1 is 1/4 x take away 1/2. If you add 1 to both sides, kind of rushing through that, but want to get in time, so we're good. You're comfortable with that process? Finding an equation in a tangent line is really just find the first derivative, evaluate it at whatever this x coordinate is, and that gets you the slope. And you already know the coordinates of the point P. You put them together in this equation, and you've got that. If, and I'm not doing it because I don't have enough time, but if I drew this guy, and he might look, like that, and I found the point 1, it'd probably be here. Wouldn't that red line be the equation of this tangent line? And can't you do that in Desmos and look as a check? Because if you get it wrong, wouldn't this line be up here somewhere or pointing some funny angle that wasn't meant to do? Perfect timing, I think, just about.